Morning, everyone. My name is Shen, and today I'll be talking about benchmarking TinyML systems. This presentation is based on an investigation project that myself and a partner did for our final fourth-year engineering project. So, machine learning is an expensive and energy-intense technology. It requires expensive components, such as high-end GPUs and PCs. These components also consume high amounts of energy during operation. With the recent boom in AI and ML, there's been lots of investment into large-scale, expensive cloud ML systems and solutions. But this then raises the question of, can you perform effective machine learning on a cheap compute-constrained device? Well, the short answer is yes. Low-cost, energy-efficient machine learning is possible using microcontrollers like the STM32 series. This specific discovery board over here is a 2000 Rand microcontroller board that is specialized for neural networks. It's low cost and low power, which makes it an excellent option for edge computing machine learning. In today's presentation, I'll give you a detailed overview of the investigation approach that was followed, the neural network models that were implemented, the data processing methodology, the compression methodology, and a benchmarking process, and finally, a discussion of the system, its limitations, and the applications of it. So, the aim of this investigation is to perform image anomaly detection using a data set of industrial cables, and then to benchmark the performance differences between a PC and microcontroller implementation of this. Anyway, to continue, for the investigation approach, the aim of this investigation was to perform image anomaly detection using a data set of industrial cables, and then to benchmark the difference in performances between a PC and microcontroller implementation. To do this, we used three neural network models, namely a feed-forward neural network, a 2D convolutional neural network, and an autoencoder. But I'll explain more on these later. Two systems were developed for the experiment, a full PC system and a microcontroller system. The three models were implemented on both of these systems, and they were implemented using Python and TensorFlow. For the microcontroller, the models were compressed using LightRT and the STM32Cube IDE. Anomaly prediction was then performed for the cable dataset on both systems, and we then benchmarked the results. So, coming back to those neural network models. As previously mentioned, we have a feed-forward neural network, a 2D convolutional neural network, and an autoencoder. We developed three different types of models to determine the suitability of all three of these on both systems. All three models were developed to perform binary classification, so they'll either detect that an image has an anomaly in it or it doesn't. The neural network and the 2D convolutional neural network are trained with examples of cables with and without manufacturing defects to be able to classify both of these images in the outputs. The convolutional model is more optimized than the feed-forward model because it can detect shapes and edges better than the plain normal neural network. The autoencoder performs generative analysis on trained images of cables without manufacturing defects. This allows it to generate an ideal image of what it considers to be a cable. This generated image is then compared against a real image from the dataset to determine whether or not there's an anomaly in it by comparing the differences. So here are examples from the dataset. On the left here, we can see that this is a cable with no anomalies, and on the bottom, we have cables with anomalies. These anomalies include things such as missing wire, missing casing, and any cracks that might be in the wire itself. So, to improve the training results on all of the models, we needed the images to be pre-processed. This basically means that we had to make the images smaller, and we also had to change the hue and saturation of them. For the normal neural network and the 2D convolutional neural network, all we had to do was increase the saturation of the image and slightly change the size. Whereas for the autoencoder, here you can see that the image is very pixelated because we had to drastically decrease the size of the image to be able to fit onto the microcontroller. We also had to increase the hue and saturation so that the color definition was improved. At the end here, you can see that this is the output of the autoencoder. So this is the ideal image that the autoencoder considers to be an ideal cable. And this is what it uses to compare against actual images in the dataset. So, moving on to model compression. To make the models smaller, they have to be compressed. This compression is done using quantization, where the weight values, which are 32-bit floating point values, are compressed into 8-bit precision integer values onto the microcontroller. LightRT only offers standard compression, whereas the STM software offers three compression methods, namely low, medium, and high. We used all 4 of these available options to compare the performance results. So, moving on to the benchmark metrics. The machine learning metrics were captured using a confusion matrix. I know that there's a lot of information here, but don't worry about it. The main metric that we're mainly concerned about is accuracy, which basically just means out of all of the images that we classified, how many did we classify correctly? If we take a look here, matrix 1 shows that all versions of the feed-forward neural network achieve an accuracy of 88%. Matrix 2 and 3 are for the 2D convolutional neural network. They show that for the PC version, we're able to achieve an accuracy of 96%, whereas for the compressed versions, we're able to achieve an accuracy of 97%. Matrix 4 shows the results for the autoencoder, which only achieves an accuracy of 69%, which is quite low in comparison to the other 2 models that were implemented. These results indicate 3 things. Firstly, it's possible to perform highly accurate machine learning on a compute-constrained device like a microcontroller, when using neural networks, and you can achieve the same results as on a PC system. Secondly, due to the limited flash storage of microcontrollers, it's not suitable to use autoencoders as you can't fit big image sizes on it, which is the reason why we've got such a low accuracy on this model. And finally, it's even possible to achieve higher accuracies on the compressed models than you can on the PC, because as you see here in Matrix 3, we've got 7% on these compressed models compared to 96% on the PC version. We think this is due to quantization and optimization of models when they're in integer bit form. Moving on to benchmarking speed, we benchmarked the speed of all of the models, and the results are shown here in this bar graph. As you can see, the PC is denoted by the blue bar. The PC is always going to be faster than the microcontroller, as it just has more processing power. So you can get comparable results on a microcontroller. However, if performance is really important, you need speed, the PC is going to be the better option, as the compressed models always perform slower than the PC. We also benchmark the flash storage size to see how much compression is performed. So on the left here, we've got the PC sizes, and on the right here, we've got the compressed model sizes. If you take a look here at the normal neural network versus the PC versus the compressed version, it's between 11 and 23 times greater than the size of the compressed models. If you're looking at the 2D convolutional neural network, the difference is about a 24 times size scale. And for the autoencoder, it's about a 5 times scaling factor as well. So these results show that the storage requirement for ML models can be significantly reduced when you use quantization for compression, and that you can achieve greater compression results with the STM software when compared to using LightRT. So as you see here for the normal neural network, these 2 versions were compressed with the STM software, whereas this purple bar was compressed using LightRT, and it's about a 50% difference in compression size. When we benchmark the energy, obviously a full PC is going to use more energy than a small microcontroller, but it's still important to point out the results here. The left images show that the PC uses power has a power draw between 21 and 26.5 watts, whereas the microcontroller only has a power draw between 0.3 and 0.42 watts. On average, there's a 58 times difference in the power usage between both systems, and this shows that the PC system is using significantly more energy than the microcontroller. So this low energy consumption of the microcontroller system shows that it can be energy efficient when you want to do machine learning. So what are the system limitations? Even though the results we achieved are promising, the system does have limitations. The system is not capable of real-time image anomaly detection since there is no camera in the system. We can only use and analyze pre-obtained data sets and images. Furthermore, in terms of image capture and storage, in terms of analyzing images, we can only do it in batches because of the limited flash space and storage on the microcontroller. This can be dealt with by including a micro SD card on the microcontroller. However, we didn't have one available on our model, so we can only batch images. Also, the STM software is not open source, so if it ever gets deprecated, you'd be forced to use the LightRT option, which as seen earlier does not offer the same performance results that you can get from when using the STM software. So, what are potential applications of the system? Well, as mentioned, we were detecting defects in cables. The idea of this is that you can extend it to manufactured parts on a conveyor belt. Imagine You have manufactured parts going on a conveyor belt, and they can be scanned as they're being processed to determine if there are defects. So you can remove them from the production line before they even go out for sale. Another potential application is in agriculture, where the system can be used to detect crop diseases early on before the rest of the crops gets infected. So you can analyze it with a camera, you can detect the disease, and you can remove the infected crop. So what can we conclude from this investigation? Our results show that it's possible to perform low-cost, energy-efficient machine learning with neural networks when you use an STM microcontroller. They also show that you can achieve highly accurate image anomaly detection using neural networks and 2D convolutional neural networks. The system that we developed requires more development, but it does offer a good proof of concept for what you can do when you try and perform compute-constrained machine learning. Thank you.